In many cases, we can find the area of a region by integrating in either the x or the y direction. I just want to demonstrate to you how that would work. So if you take a look at the pink region, you can see this is a fairly simple region. It's just bounded between the purple curve and the red curve. You now know that the red curve, even though I'm calling it a curve, it's just a line because a line is a special type of curve. So in order to find the area of the pink region, we would simply integrate top minus bottom like this. Write area is equal to the integral. You can see that on the left we're bounded by x equals 1, on the right by x equals 2. That's here and here. So we simply integrate the top function minus the bottom function. Bottom function happens to be a negative number, so we get here top minus bottom, and that's our integral. And by the way, if you wanted to simplify that, there would be nothing wrong with writing the integral from 1 to 2 of 1 over x plus 1 plus 1, since minus the negative simplifies to that. That would be equally correct. So perhaps the more interesting problem here is to try to write this integral using the variable y. In other words, do it in the dy direction. So I've put up the same graph. Now we're going to try to write the same integral in the dy direction. So recall that when we do this in the y direction, what we're doing is we're going to be adding up rectangles like this, which have little tiny bits of height dy, like that. Sorry, that's not a 3, it's a bracket I'm trying to write there. So what we need to do is we need to identify the left and right functions and see what the top and bottom are in order to find the limits of integration. So the thing to notice here, actually let me put the points in, make it a little easier. We can easily see that this point here, since the curve is y equals 1 over x plus 1, this is the line x equals 2. So this point is going to be 2, comma, if I plug in a 2 into this function, I get 1 over 3. And this point here, since this is over the line x equals 1, this is going to be the point 1, comma, 1 over 1 plus 1 is 1 half. So the significance of this is take a look at, which color do I want to use? Take a look at where the left and right boundaries are. For the entire pink region, this is the left boundary. But depending on where you are in the region, the left boundary, in fact specifically depending on whether you are above or below this dotted line, the right boundary rather, is going to be either the green vertical line or the purple curve. So we actually need to split this up into two integrals in order to do it in the y direction. So let's do the lower part of the integral. Sorry. There we go. So let's say area. So we want to start, we want to find the lowest possible y value, and we can easily see that that's y equals -1. That's the bottom of the region. And we want to integrate first up to the dotted line. And that dotted line is, you can see the y value there is 1/3, so this is going to be y equals 1/3. That's the horizontal line that we're integrating up to. And as you can see, the right function is just x equals 2 and the left function is x equals 1. We barely need an integral for this, but we're going to write it out formally anyway. So you can see that this is the right function and this is the left function. Okay, so now what we need to do is we need to write out the integral for the second part for the upper part of the pink region. So we're going to add, integral. So we need to write out what the upper and lower limits of integration are. So first of all, we can see that as we were proceeding upward from -1 up to this horizontal line y equals 1/3, that's where we stopped. So that's where we need to keep going from. So we're going to start again at 1/3. And then from there, we need to go up to the top of the region. And what you can see is that's going to be up to this horizontal line. The y part of the coordinate gives us the y value of that line, so that's going to be 1/2. And so we integrate from 1/3 up to 1/2, and then we do right minus left. So the problem is, since we have this purple curve, you might think that what I do here is I write 1 over x plus 1, but of course that's not correct, because I need to have a curve in terms of y, which means that I need to take the original equation and solve it and solve for x in terms of y. So let's just write out the equation here, and then I'll do a whole bunch of algebra really fast. And that's the same curve in with x as a function of y, so it's x equals 1 over y minus 1. So let me actually give myself a little more space here. So that's going to be 1 over y minus 1 minus, and then once again I still use the left boundary, left curve. Excuse me. Still use the left curve, and that gives me minus 1 dy, and here I'll just put this in, that this is the right curve and this is the left curve. So there we go. That's the integral, or really the sum of integrals. If we ask for an integral, sometimes it's actually going to be a sum of two integrals. So this is the area of the same region written in the y direction. As you can see, it's often the case that one direction is much more complicated than the other, but if you truly want to understand how these integrals work and how to set them up, which is usually far more important than being able to calculate them, you should really understand how to do it in either variable. Now let me show you a different type of problem. In this case, what we're given is an integral that gives the area of a region, and what we want to do is write an integral in a different variable that gives the area of the same region. So the integral is, of course, 0 to 3 of e to the 2x minus 1 dx. If you think about what that integral looks like, by now, with understanding that that in the x direction we use the top minus bottom paradigm, you should be able to spot fairly quickly what region this is giving the area of. Let's just quickly draw it out. See, is that if I have the curve e to the 2x, which looks like that, and some of you should recognize that e to the 2x has a y-intercept of 1, and then on the bottom I have just the horizontal line y equals 1, so I'll just put these in here. That's going to be top, that's going to be bottom, and I'm integrating it from 0 to 3, so I'm going all the way up from here, 0, up to 3, like that. So essentially, this is the region that I'm finding the area of. Just put in the names of the curve. That's going to be y equals e to the 2x, and this is going to be y equals 1. So what we want to do is look at that region and see if we can rewrite the curve, rewrite an integral for the area of that region using y as a variable. So let's see what we have here. We know that we're going to need to know the upper and lower boundaries of this region in order to write the integral in the y direction. So let's see. It looks like the top boundary is going to be that horizontal line, and of course the lower part of the y integral is going to be given just by the line y equals 1. So let's find this point here. Since the function is y equals e to the 2x, and this is the line x equals 3, that means that this point is going to be 3 comma e to the 2 times 3 is e to the 6th. So that point is e to the 6th, and this line itself is just y equals e to the 6th. I know that that's not a convenient number, but at this level of math you should really get used to the idea that e to the 6th is every bit as much a number as something like 2 or 3 or 4 is, and there's nothing special about working with that kind of number. Okay, so let's put in the left and right boundaries. What you can see is that this is going to be the right boundary. That's the purple curve. The line x equals 3 gives you the right boundary, and the purple curve gives you the left boundary. As we know from the previous example, we're going to have to solve for we're eventually going to have to solve for x in terms of y, so that we can rewrite that purple curve as y as a function of x. But let's just start to write out the integral. So we can see that the area Since we're writing this in the y direction, the lowest possible y value is given by this green horizontal line, and that's y equals 1. And the highest possible y value is given by the red horizontal dotted line, which is y equals e to the sixth. So we're integrating from 1 up to e to the sixth. Now we can see that the right boundary is just the horizontal line x equals 3. And the left boundary is going to be that curve. So let's just solve for that. And by the way, if you've gotten this far, there's a little bit of a fancy thing that I can do here. Some of you will recognize that by the properties of logarithms, that's going to equal ln of y to the 1/2. So I can actually rewrite this as x equals ln of the square root of y. So either that or that would give you the curve, would give you a correct expression for the curve. So in any event, let's use the lower one just because it looks a little bit cleaner. It's certainly not required. So we can see that the left curve, which we're going to subtract, is ln the square root of y dy. I'll put this in. That's going to be the right, and that's going to be the left. And we can see that therefore that is a y integral for the same region as this is an x integral.